Hey guys, will you take a few minutes with me so that we can start 3-6A now? That way we'll have more time in class tomorrow to actually do the examples together. What we're going to talk about is some what we call curve sketching, where we're going to take all of our different features of our graphs. Is it increasing? Is it decreasing? Is it concave up? Is it concave down? Do we have relative maxes, relative mins? Do we have points of inflection? All of that good stuff. Find it all by hand. Can we put it all onto a graph and kind of sketch what the graph would look like? Without having to put it in our calculator, could we sketch what the graph would look like? Okay, so before we get into examples, what I'd like to do is I'd like to fill out this chart with you. There's 3 different columns. The first column is about a feature. What feature on a graph? We have a whole bunch of features on a graph. For example, like x-intercepts, y-intercepts, stuff like that. What do they mean? Okay, what does it mean to be an x-intercept? What does it mean to be a y-intercept? What does it mean to be a relative max or a relative min? And then how would I get those different things? How would I get the x-intercept? How would I get the y-intercept? Stuff like that. If we can fill out this chart, that'll kind of refresh our memories about all the different things, all the different features of a graph. And then when we get into class tomorrow, we can do some of the examples together and apply those features to graph these different functions. Okay? So here we go. The first feature we're going to talk about is an x-intercept. Okay, what does an x-intercept mean? Well, an x-intercept means where the function crosses the x-axis, right? If I have an x-intercept, it means it touches the x-axis. Maybe it doesn't cross all the way through, but it does touch the x-axis somewhere. To find the x-intercepts, we would plug in 0 for y. We plug in a 0 for y into our original function, and we would solve for x. We'd get a bunch of x equals, and that would mean where does it touch on the x-axis. Okay? So the next feature we're going to talk about, where does it touch on the y-axis? If it touches the y-axis, what's that called? A y-intercept, right? And so how would I get the y-intercept of a graph? Well, I'd plug in 0 for x. I'd plug in 0 anywhere I see an x, I'd solve, and I get a whole bunch of y equals. That's where I touch the y-axis. X-intercepts, y-intercepts. Okay? The next thing, domain. Domain means all of the x values. Okay? What x values work in our function? Okay? There are some times where x values do not exist or don't work. For example, if we have a denominator. If we get a 0 in our denominator, we end up with a vertical asymptote, right? Or remember, if there's a hole, if there's anything on top that cancels with anything on bottom, then there's a hole there, which means I have no x value. That x value is not in the domain. Okay? Some other things we have to worry about are maybe radicals. Okay, we've seen this come up a few times. If I have a radical in my function, what are we not allowed to have underneath a radical? Negatives, right? We're not allowed to have negatives underneath our radical, or else we end up getting imaginary numbers, and we're not dealing with imaginary numbers. We have a hard enough time doing regular numbers. Okay? So look at your original function and make sure there's no domain issues or restraints. So denominators, radicals, stuff like that. Okay? All right. If there are any holes or if there are any asymptotes, that's going to cause a problem in your continuity. Is your function continuous? Do you have holes? Do you have asymptotes? Do you have gaps? Okay. We just talked about vertical asymptotes. Vertical asymptotes happen when the bottom equals 0. Holes happen when something on top cancels with something on bottom. So if you factor your numerator and your denominator and something on top cancels with something on bottom, then you've just found a hole in your graph, which causes discontinuity. Okay? All right, horizontal lines that the graph gets close to but never touches. Okay, horizontal lines that your graph gets close to but never touches are called horizontal asymptotes. Okay, we have vertical asymptotes. We also have horizontal asymptotes. And we talked about this a while back, how to find horizontal asymptotes. We find horizontal asymptotes by looking at degrees, degree of your numerator versus the degree of your denominator. When the degree of your numerator is greater than the degree of your denominator, when p is greater than q, then you have no horizontal asymptote. When the degree of your numerator is less than the degree of your denominator, if p is less than q, then you have a horizontal asymptote at y equals 0. Your graph's going to get really close to the x-axis. It's always going to, it's kind of going to level off. It's never going to touch it. It's going to be a horizontal asymptote there. Okay? If your degree of your top is equal to the degree of your bottom, then you have a horizontal asymptote at y equals the coefficient of your top divided by the coefficient of your bottom. Coefficient meaning the number in front. So you would divide those two numbers and you would get your horizontal asymptote there. Okay, horizontal asymptotes. First derivative. What does the first derivative tell us? Well, the first derivative tells us when our function is either going to increase or decrease. If your first derivative is positive, then your function is increasing. If your first derivative values are negative, then your function is decreasing. So how can we tell if it increases or decreases? Well, the first thing we have to do is find our critical numbers. And we find our critical numbers by taking our first derivative and setting it equal to 0, or where it doesn't exist. Don't forget about that second piece. So where does your first derivative equal 0? The top equals 0. And where does your first derivative not exist? Your bottom equal to 0. That's going to get you your critical numbers. Then you can test your intervals, your values in between, and you can see if it's positive or negative, increasing or decreasing. Okay? All right, what do I set equal to 0 to get possible points of inflection? Points of inflection are found in my second derivative, right? Second derivative tells me if my function is concave up or concave down. If my second derivative values are negative, I'm concave down. If my second derivative values are positive, I'm concave up. If I take my second derivative and set it equal to 0, then I have possible points of inflection. They are only truly points of inflection, though, when I have a sign change in my second derivative, if I change concavity. All right, maximums or minimums. These are called relative extrema. You have relative extrema or local extrema. Then we have absolute extrema if we wanted to find absolute maximums or minimums. Okay? In order to find relative maximums or minimums, we have to find our critical numbers first. That's when I set the first derivative equal to 0 or doesn't exist. That should be on there also. And then make sure you check your values, because I can't be a maximum, a relative maximum, unless I change from increasing to decreasing. I can't be a relative minimum unless I change from decreasing to increasing. So you have to make sure you test your values. If you do not have a sign change in your first derivative, then it is not a maximum or a minimum. Okay? All right, next thing, concavity. Okay, concave up, concave down. It's kind of like a hill or a valley. Okay, you can use whatever description you want there to describe concavity. We find concavity by setting our second derivative equal to 0 or does not exist. I keep forgetting that second part, so please don't forget about that. And then checking your values. If your second derivative is positive, again, concave up. If your second derivative is negative, then it's concave down. But you have to test your values because it doesn't always change concavities at your points. All right, points of inflection, where f changes concavity, where your function changes from concave up to concave down. I know that there's a point of inflection when I set my derivative equal to 0 or does not exist and then check my values, and only if there is a sign change in my second derivative, I can call it a point of inflection. If there is no sign change, then it is not a point of inflection because it doesn't change concavity. Okay. The last thing we just got done talking about is limits as we go to infinity. Okay, as we are approaching way left into our graph, as we're approaching negative infinity, what's happening with our graph? Or as we're going way to the right of our graph, what's happening? So I can find out what's going on in the meat of my graph, right in the middle. But could we also describe what's happening as we go really far left and really far right, as we approach positive infinity or negative infinity? Okay? In order to figure out what's going on to the right or to the left, then we're going to evaluate that limit. We're going to look for horizontal asymptotes. We're going to see if there is a horizontal asymptote, and that will be our limit as we go from negative infinity or to positive infinity. Okay, so we're going to evaluate our limit there. Lots of good stuff on this table of values, on this T-chart, whatever you want to call it. This is probably a good thing to study, like a little cheat sheet that you could use. You can cut out, you can take a picture of. Lots of good things that we've been talking about in calculus that are good to know, not only for our lesson tomorrow, but for always. Okay, so make sure that you know all these different characteristics of a graph, and what we're going to do is we're going to put them all together and start graphing these things without having to look at the calculator. Could we find all of these features and put it onto a graph? Okay, all right, I'll see you guys tomorrow.